We continue our lecture videos on Laplace transforms for differential equations, and in this session we are taking linear ordinary differential equations, where we've talked about having it as either first order, higher order, or systems. We've looked at techniques in solving all these, and what we're doing is to take examples of this and solve with what the Laplace transforms and see what we are going to get. We are going to use certain establishment like equation 1, which is a simply Laplace transform of a given function, equation 2, which is the Laplace transform of derivatives. We'll also make use of the inverse Laplace transformations, where we have to use the partial derivatives, or if it's a common function, we know its inverse. So let me take the first example on first order. Let's consider a simple population growth rate or model, where we want to say that the population growth is proportional to the population at the current time. It means I have a first order of the form where my K is the carrying capacity. This is my first order. Let's add some initial conditions. Because the order is 1, it means I will need just one initial condition. If you want to solve this, I'll use the two forms. Someone will want to solve this using the usual first order technique. I'm going to use separable, and you know why? Because this is separable, it means I can have it as 1 over y is equal to k dt. dy dt is equal to ky. That is the differential form, or the standard form, sorry. So I can separate it this way. What do? I integrate both sides, and I get y ln y is equal to kt plus some constant of integration. I can simply find exponential of both sides. So let me quickly do that, and then you're not going to get something as this. Okay, y of t. Now I want to solve at the initial condition given, that is y at 0 equal to some y naught. It means I'm looking for a particular solution, and we're simply going to have this as some y naught e. You can all have this solution, so I wouldn't want to waste time on that. Now assuming I want to solve this same problem with the Laplace transform, what do? First, you take Laplace transform of the entire expression. So Laplace transform of the given differential equation. So I have Laplace transform of the first derivative is equal to the Laplace transform of my right hand side. I have to now do my evaluations of the derivatives. Now that is going to make use of equation 2 for my derivative. This is going to be s the first, so I'm going to use capital Y-S. If I have y, I'm going to use big Y, and if I have small f, I'm going to use big F. That is it. Minus f of 0, so it means y at 0 is equal to, this is a constant, so it comes out as k. This is the same as k Laplace transform of my y, which will simply be the big Y of s in the frequency form. I can group like terms. I'm going to have s minus k, taking the frequency is equal to y at 0. If I want the big Y of s, it's simply y naught. Y at 0 is y naught all over s minus k. That is the substitution of the initial condition. This is the frequency domain, and so this is not the solution. This is in the frequency domain. We must get a solution back in time. So what do? We take the inverse Laplace transform of the problem. It means that inverse of the big Y of s equated to the inverse of y naught over s minus k. This inverse simply gives me back in time, and I can have y naught, which is a constant, out. I'm taking Laplace inverse of 1 over s minus k. Do you use partial fractions here, or do you check your Laplace table? This is a common function for the exponential. So this is y naught exponential kt. Why is it that? You realize that from the table, Laplace transform of exponential function is 1 over s minus a. So a Laplace transform of ekt is as if my a is what? K. A is equal to k. That is why I have it as exponential kt. Are they the same? Yes. So whichever technique you are using, you're going to get the same answer. So which one is easier for you, the Laplace approach or all the techniques you've learned? Let me take the second example on higher order. So example 2, I'm going to take the higher order differential equation. Here I'm going to take the homogeneous part of it, not the non-homogeneous. We'll take that later. Let's consider a simple Newton's second law, which is the Hooke's law. Hooke's law is about harmonic motion of spring and masses. It says that the force of a spring is proportional to displacement. So you know this is an application of second order. I can have it written as some x prime plus the angular velocity is equal to 0. This is the model for the Hooke's law of motion. Now how do you solve this? This is not first, this is second order. It is linear and it is homogeneous. Okay, so how would you have solved this? I'll take it through. Someone will use we have a common solution technique, that is the root solution, because it is homogeneous. What do? I find the root. I first find the characteristic equation, which will give me lambda square omega squared plus omega squared equal to 0. And you know this is going to be lambda squared is equal to negative omega squared, and hence lambda is equal to plus or minus omega I. Because of the negative, I added I. And so quickly, you know the root here is a complex root. And I can write the solution as, we are using x, so x of t is equal to some EAT C1 cos dt plus C2 sine dt. From here, I have my a at 0. It means I have the real part at 0. We get C1 cos omega t plus C2 sine omega t. That is my solution. The question is it the same case as the Laplace transform? I'll change the pen to blue. Let's use Laplace transform here. It means I take the transform on the equation. So Laplace transform of the second derivative plus Laplace transform of the omega square x is equal to 0. Second derivative, I'm going to get s squared, the big S, minus, you know, x reduces in order, the first derivative root minus the second term, which will be the first that, plus this is omega square as a constant out. I get my frequency domain as this. So this is the same as omega square because a constant. I take the Laplace of the dependent variable. Now, what are the conditions we want to assign to a differential equation? Because it's a second order, it means we need two initial value or initial conditions. This is IVP. I'll take the first condition as x naught. I'll take the second condition as x1. So this is part of the problem. Okay, let's continue. If I want to group like terms, you realize I have some s squared plus omega squared. The big frequency is equal to, every other term goes to the right hand side. I have s x at 0 plus x prime at 0. So let me just quickly do a substitution. You know x naught is some x naught, and then the derivative is some x1, small letter x1. So I just do the substitution of the conditions in here. Now I can have my frequency of the x given as whatever I have on my right hand side all over the coefficients. This is what I have. This is a solution in frequency domain, and hence I have to take the inverse Laplace transform. So the next is to take the inverse Laplace transform of the problem. So Laplace inverse of my big X is equal to Laplace inverse of everything here. Don't get scared when you have these representations. You must be smart and checking your Laplace table. If you see any common function, you use it. If not, you go through the partial approach. I know that's simply going to give me my x in terms of t. Frequency moves back to time. But what about this part? This part is in two forms. I have, because it's addition, I have Laplace inverse of s naught over s squared plus omega squared, and I have Laplace inverse of x1 over s squared plus omega squared. So I've explained why I'm splitting. It's as if I'm dividing through the terms. So it means my x of t will be equated to, I can have s as a constant out, Laplace inverse of, x naught is the constant, not the s. X naught is the condition we would know, so it can come out this way. I have s over the remaining terms. The same thing here, my x1 comes out, and I have Laplace inverse of 1 over s squared plus omega squared. So I go to my Laplace table. Do I see a common function to represent here? Yes. This is a cos function, or cos Laplace. So this is the same as cos omega t. Why? From the Laplace table, Laplace of cos at is equal to s over s squared plus a squared. So it's as if when my a is equal to omega, it means I'm going to get s over s squared plus omega squared. That is what I have it as, Laplace of cos omega t. And so what will be the other term? We would wish it to be sine at, because Laplace of sine at is equal to the a over s squared plus a squared. Note the difference. Cos is the s, sine is the a. But if I want to compare this to whatever I have here, that is 1 over s squared plus a squared. It means that the only way to get a up is to divide this by a and have it as a over s squared plus a squared. This is the same as that. 1 over s squared plus a squared is the same as 1 over a over the terms. And so it means I'll have this one as plus some x1 over the omega. Then I can have the Laplace inverse of omega over s squared plus omega squared. And that should give me my sine part of the problem. So let me clean this arrow and have it as cos wt. This is my solution in the Laplace domain, and this is correct. But someone will say, when I use the root equation, I don't get anything similar to the Laplace solution. You see I have some x naught here. I have x1 over omega. This means that in my form here, my c1 is equal to my x naught, and then my c2 is equal to my x1 over omega. Someone might not still be convinced, so let's go through that. If I want to work out with the initial conditions given, such that x at 0 is equal to x naught, x prime at 0 is equal to x1, what do? at the first initial condition. So initial condition 1, everywhere I see t, I have it as what, 0. And so x at 0 is equal to c1 cos, everything goes to 0, plus c2 sine 0. This is the same as x naught is equal to sine 0 is 0, cos 0 is 1. So I have it as c1. Have we proved that? Yes. The second initial condition, so initial condition 2, it says that my x prime, so first I have to differentiate xt. So x prime of t is going to be negative c1 omega sine. You know how to differentiate your cos and sines, plus c2 omega cos. Okay, now I can look at the second derivative as 0, which means I'm going to get c1 omega sine 0 plus c2 omega cos 0. What is x prime at 0? It is x1 is equal to, you know, sine 0 is 0, cos 0 is 1. So I have it as c2 omega. This means that my c2 is equal to what? Some x1 over omega, and we've established that too. So indeed, if I have to work with the conditions given, my c1 is x naught, and my c2 is the x1 over omega, and I'll get the same solution as I had in the Laplace. I first didn't work it out because someone will say, because I already have the solutions, I will try to get it with the Laplace. No, that is why I paused here and I went to use the Laplace to see what this coefficient would be. Okay, in the next example, that will be example 3. Someone will say, okay, what if I have a higher order, but now it is a non-homogeneous equation? A non-homogeneous, you have to use two techniques, either the method of method of undetermined coefficients or variation of parameters. You know when to use this, you know when to use that. And trust me, it will be the same approach. Take the Laplace transform of the given differential equation, do your substitutions of the initial conditions given, group like terms, find the inverse Laplace transforms, and then that is your solution at the end of the day. So the whole idea of solving Laplace with differential equations is such that we have a real problem which we think that finding the direct solution here will be difficult too, as we established from the transformations. So what do? In the real problem, I go to a different state where I'm going through some transformations. So this transformation is the Laplace transformation. It is easier to solve in this form. I get some solution in the frequency domain. I need to get this. So to get that, I have to go through the inverse transformation, which may take me back to my solution in terms of what? Time t. So this is the whole idea for Laplace transform. In the last video, I'll take examples of solving Laplace transform with systems of equation. Stay tuned.